This lesson is going to be from your textbook, lesson 8-1. We're going to introduce the imaginary unit I. I will talk more about this and give you notes on this in just a second, but I do want to spend just a few minutes talking to you about where imaginary numbers come from. So what we've been working on in the past with factoring is we've been concentrating on the kind of parabolas that intersect the x-axis twice. Okay, so this is the kind of parabolas we've been working with. Here's what we've been doing with them. We give it to you right here in its standard form, and then we ask you to factor it, and you'll notice right here that you can tell for sure that it's the same function, because if I turn that off, hold on, let me turn that off. There it is. Turn the red one off, you can see the blue one graphed. Turn the red one back on, they're graphed right on top of each other. So these two graphs are the exact same graph. This is the standard form. This is the factored form. I would have factored this using an easy table. Why would I have factored it using an easy table? Because of that leading coefficient being 1. So what I would have looked for factors of 5 that have a sum of -4. I would have found out that that was +1 and a -5. Then what those factors would have told me, I would have set each one of those factors equal to 0. And I can do that for you real quick. This is just a review. This is what we've been doing. I would have taken that x plus 1 and set it equal to 0, and I would have taken that x minus 5 and set it equal to 0 using the zero product property. Now subtract 1 from both sides to solve that one. Add 5 to both sides to solve that one. And I found that the x-intercepts right here, well, this should be a -1. The x-intercepts here and here are where that graph crosses the x-axis. Those solutions are the x-intercepts, okay? So that's what you have learned how to do. Now, that's not the only kind of problem that we learned how to work. We also learned how to work the problem that only intersects the x-axis one time. That problem, here's the factored form of it, that problem's always going to be a perfect square because it's only going to have one solution, and the only way a quadratic can only have one real solution is if it's a double root, okay? So we factored it. We used the easy table because the leading coefficient right there was 1. We used the easy table, and we looked for factors of 4 that have a sum of -4. We found the two factors are -2 and -2. You set x equals -2 equal to 0, and you find out that 2 is the x-intercept. And 2 is the only x-intercept because it's said to be a double root because we had 2. Now like I said, that's nothing new. We've learned, we already know how to do that. But now we need to learn what to do about this kind of problem, okay? So if I look at this parabola and I see, okay, I'm going to try to factor this one. It has an easy table. I can do a factors of 9. Factors of 9. And we need a sum of -4. Factors of 9 are 1 and 9. We can make them both negative since it needs a negative sum. And we can do 1 and 9 and 3 and 3. Those are the only factors of 9. So if I do -1 plus -9, I get -10. And -3 plus -3, I get -6. There are no other factors of 9, so I cannot factor this problem. It's not factorable. So all that tells me is that the fact that it's not factorable tells me that it's not going to cross the x-axis, which means it has no real solutions. Okay? But it does have solutions. And then the next little video that I'm going to show you is kind of going to it's going to explain a little bit about why this is not crossing the x-axis, but it still has solutions, and how we come up with the name imaginary. So hang on just a second.
Let's say we're given the function f of x is equal to x squared plus 1. We can graph our function and get a nice parabola. Now, let's say we want to figure out where the equation equals 0. We want to find the roots. On our plot, this should be where the function crosses the x-axis. As we can see, our parabola actually never crosses the x-axis, so according to our plot, there are no solutions to the equation x squared plus 1 is equal to 0. But there's a small problem. A little over 200 years ago, a smart guy named Gauss proved that every polynomial equation of degree n has exactly n roots. Our polynomial has a highest power, or degree, of 2, so we should have 2 roots. And Gauss's discovery is not just some random rule. Today we call it the fundamental theorem of algebra. So our plot seems to disagree with something so important, it's called the fundamental theorem of algebra, which might be a problem. What Gauss is telling us here is that there are 2 perfectly good values of x that we could plug into our function and get 0 out. Where could these 2 missing roots be? The short answer here is that we don't have enough numbers. We typically think of numbers existing on a one-dimensional continuum, the number line. All our friends are here. 0, 1, negative numbers, fractions, and even irrational numbers like root 2 show up. But this system is incomplete. And our missing numbers are not just further left or right, they live in a whole new dimension. Algebraically, this new dimension has everything to do with a problem that was considered impossible for over 2,000 years, the square root of -1. When we include this missing dimension in our analysis, our parabola gets way more interesting. Now that our input numbers are in their full 2-dimensional form, we can see how our function x squared plus 1 really behaves. Our function does cross the x-axis. We were just looking in the wrong dimension. So why is this extra dimension that numbers possess not common knowledge? Part of the reason is that it has been given a terrible, terrible name. A name that suggests that these numbers aren't even real. In fact, Gauss himself had something to say about this naming convention. So yes, our missing dimension is comprised of numbers that have been given the ridiculous name imaginary. Gauss proposed these numbers should instead be given the name lateral, so from here on, let's let lateral mean imaginary. To get a better handle on imaginary, I mean lateral numbers, and really understand what's going on here, let's spend a little more time thinking about numbers themselves. Early humans really only had use for the natural numbers, that is 1, 2, 3, and so on.
Okay, I'm going to stop it right here. Not that what he has, and I will give you the link to his entire video, but what he has right here is extremely interesting. However, my first video is getting a little long, and I want to tell you, make sure you understand that even though the guy doing this video proposes that we call imaginary numbers lateral numbers, we don't. We call them imaginary numbers. And that leads me to the definition of, I think it's over here on the next page. Yes, on page 122, this is your definition right here. An imaginary number is defined to be the square root of -1. Okay, they make it really simple. They make the number 1 be the number that's in there with the negative because It doesn't have any other factors. And we know that if we are trying to find a number that multiplies times itself to give us -1, we can't find that because a positive times a positive equals a positive and a negative times a negative equals a positive. So there's no way we can multiply a number times itself and give us -1. So anytime we run into the square root of -1, we're going to not put the square root of -1 and instead put an I. I'm going to stop this video here and I will start the next video with showing you what I mean by replacing numbers with an I, replacing the value of the square root of -1 with an I. That's what's coming up in the next video.